Okay, this example says find the turning points of this curve and identify their nature. Well, turning points are when dy dx, the slope of the curve, is 0. That should be a flat top there. So there's an example of a local maximum or a minimum. A curve can also come up and twist back on itself, and also that's when it flattens out. So whenever it flattens out, that's a turning point. It turns either around like that way, or turns around and then flips back up on itself. So can you see the gradient is 0 there? So that's why dy dx is equal to 0 in all these cases. Now here, the gradient was positive on this side and the gradient is negative on this side. So the rate of change of gradient is decreasing, isn't it? Because it was positive, 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 0. So it's slowing down and decelerating, so it's a negative. That's why the second derivative, this is just a way of writing d by dx of dy dx. So instead of us writing the second derivative like in this cumbersome way, we just use this notation to denote the second derivative. So can you say, because the gradient goes from positive value to negative, that the second derivative, that's the rate of change of the gradient, is decreasing, is negative. Yeah. Similarly, if you look at this one, you can see here that for a minimum, illustrated here, dy dx is not here, but the rate of change of the gradient is going from negative, 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 0, positive, positive, positive. So the second derivative, the rate of change of the gradient with respect to x, is on the increase, isn't it? So it's positive. So that's how you remember it. Okay, now the point of inflection, that's when it flattens out and then twists back on itself. So it could either go that way or it could go the other way. Flattens out and twists back on itself. Basically, you can see that at these points dy dx is 0. And then look at the gradient here. It's positive. Then it decreases to 0. And then it twists back up. So here it's positive dy dx. And that d2y dx squared equals 0 and changes sign. This bit should go down here, shouldn't it? Can you see the rate of change of gradient? Positive down to 0. So it was decreasing here, and then it then goes from 0 and increases. So positive rate of change here, negative slowing down here. So the gradient is slowing down, so this would be negative on this side, and this would be positive on this side, but d2y by dx squared is also must equal 0 there. Okay, and on the other side, here, so we've got, what have we got? We've got dy dx is not here, of course, because it flattens out. This side, is negative, 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 but it's increasing to 0. And then it's going from 0 and then decreasing again. So it was increase and then decreasing. So positive on this side, negative on that side. It changes, the second derivative changes sign, equals 0 there. So this is just the formula. I've just briefly tried to give an overview of what it is in terms of the pictures. So that's what we've got. Let's have a look at this problem then and see if we can see that it's not so difficult. That's the bookwork. Now let's have a look at how we do it in practice then. So let's get dy dx. Finding the turning points then, which is when dy dx is 0. So here differentiate, 3 comes down to be with the 2 to make 6, x to the 1 less, minus 2 comes down to be with the 3, x to the 1 less, x goes to 1, minus 12 lots of 1 is minus 12, and the constant goes to 0. Let it equal 0. Now there's a 6 common here. We've got x squared minus x minus 2. This factorizes. We've got an x and an x. We've done factorization in a previous chapter. I'm going to try two ones because it has to be 2 and 1, doesn't it, to give 2. This is minus, so make this minus, make this plus. So we get that. This equals 0 when x plus 1 equals 0, or x minus 2 equals 0. And this happens when x equals, move the 1 over, minus 1, or it happens when x equals 2. So we've got two turning points at x equals minus 1 and 2. Now we'll get the second derivative, d2y by dx squared. Differentiate this then. The 2 comes down with the 6 to make 12, x to the 1 less. The x goes to 1, minus 6 lots of 1 is minus 6, and the constant goes to 0. Now, 12x minus 6, when x is minus 1, and we've got 12x minus 6 when x is 2. This one, minus 18, and this one, 24 minus 6 is 18. This is negative, so this one is a max, and this one's positive, so this is a min, isn't it? Because it's the second derivative at the value x equals minus 1. When x equals minus 1, the second derivative is negative, so it's a max. And when x was equal to 2, put that into the second derivative. We get positive, so it's a min. So that's the x value. There's the second derivative, so we know it's max and min. The turning point itself was when x equals minus 1 and x equals 2. Well, we need the y values, don't we? So let's input these to get the actual turning point itself, the y value of it. 2x cubed minus 3x squared, 2x cubed minus 3x squared minus 12x. Let's have a look again. Plus 1. 2x cubed minus 3x squared minus 12x. We're just getting the y values now. Put minus 1 in for the input value for the x and put 2 in here. So what's the y value? That's minus 2. So that's minus 2. This is 1. That's going to be minus 3 then. This is plus 12. Plus 1. 13, 10, 8. Okay. And this one, 8, 16, 4, 12, minus 24, plus 1. 4 plus 1 is 4, rather. Minus 24 is minus 20, plus 1 is minus 19. So we have a max at the minus 1 point. Minus 1, the coordinate is minus 1, 8. And a min at 2 minus 19. Let me just check that in the example. Okie dokie.